This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 1, Problem Type 2. So go ahead and click on that game. So the first thing we'd want to do normally would be to go through the introductory tutorial that provides a lot of the basic information you need to learn to solve these types of problems. Now, assuming we've done that, it's also a great idea to look at some examples here. So normally I would strongly recommend that you click on the Show Example button to show examples that will help you learn how to do the problems before you actually start trying to do it yourself. Okay, assuming we've done that, for brevity I'm just going to jump straight into a game. So here is a circuit, and we have some instructions here which basically outline what we need to do. And you can always bring those up from the help menu if you need that. So we notice that we have an operational amplifier here pointing to the right, which is this triangle shaped schematic. And remember that inside there we basically have an almost infinite input impedance between the positive and negative inputs. So there's no current going into the negative terminal or into the positive terminal or into the negative terminal or coming out, either one. And there's also a voltage controlled voltage source which is connected from ground to the output, and that has a certain gain times the V plus minus the V minus. However, the gain is in the ideal sense infinite, which means effectively that makes, since this voltage has to be finite in order to avoid saturating the op amp, this voltage therefore is that finite value divided by an infinite gain, which means it has to be zero. So basically there is effectively a short between the input and the output here. And the output, of course, being the output of a voltage source, can be whatever it needs to be, at least in principle. So we might recognize this as, first of all, having proper negative feedback from the output back to the negative input, which you always need to have in an op amp circuit that's not, say, an oscillator or something like that, which isn't stable. And furthermore, we can also notice that unlike the first problem type where we had our input voltage source, which represents our input, there it was connected through a resistor to the negative input. Here it's actually connected directly to the positive input. That means this is going to be called a non-inverting amplifier, which means it'll have a positive gain. And in fact, there's actually a formula for that gain in the introductory tutorial. It's just 1 plus the feedback resistor, 9 ohms, divided by 6. So we could actually predict right away that it's going to be 1 plus 9/6 is also 3 halves, so that's basically a gain of 2.5. So the output would just be 2.5 times 5, and that actually solves the problem for us. But we'll come back to that later. Right now I'm just going to show you a more systematic way of actually writing all the equations and solving them. Also, I'll point out that there are multiple ground symbols here. That means that there is an implicit connection between these 2 points in the circuit, and there's also a connection to, although it's not really connected to the op amp, but in effect it is through the power supplies that are connected to the op amp, which are not shown here. So the ground really is connected to the positive and negative power supplies, which are always necessary to run an op amp. Okay, so we're going to go ahead and solve this. We're going to use a nodal analysis type of technique. We're not going to select a ground here as we normally do, because that also is the ground of the op amp circuit itself, in effect, again through the power supplies, and we don't want to change that. So we're going to do only nodal analysis. Mesh analysis, again, is generally not possible. So we're going to begin by doing a voltage constraint equation, since we do have a voltage source, as we would always do in a DC nodal analysis, which hopefully you've already studied to learn most of this. So that just says that V1 minus 0 equals 5, so that's just V1 basically, equals 5, and we'll just fill in those blanks there. To V1 equals, I'm sorry, that's a plus sign, equals to 5, and we can just check that equation, and that will be correct. And it also reminds us of the other types of equations that we will need to write. Now, the next type, which is unique to op amps, is something called the input constraint voltage equation. And basically that just implements the fact that this voltage must equal this voltage due to the large negative feedback that's internal to the op-amp. And again, that's explained in the introductory tutorial. But basically it means that this voltage must equal that one. And so we can basically say, there's various ways of writing it. I'll write it just with a difference term there and say that that's equal to 0. So basically V1 minus V2 is equal to 0. Or we could, of course, just as well write it as V2 minus V1 equals 0 because it's basically the same equation. Okay, so we'll check that. And that is an essential constraint in order to be able to solve a problem with op-amps. Then we pass to writing KCL equations, knowing that Kirchhoff's current law is the foundation of nodal analysis. It's really just a systematic application of that. So we'll select KCL equations to add node currents. And we'll observe, first of all, that we cannot write a KCL equation for node 1 because it has a voltage source attached, namely the 5-volt source, whose current we do not know a priori. Although, well, we kind of do here. It's going to be 0 because that current can't be anything but 0 simply because there's no current going through the positive terminal of the op-amp. So it's actually 0. But in any case, we don't write a KCL equation there because we don't need it. And node 3, which is connected to the output of the op-amp, we cannot write it there either because remember that that output represents internally the output of a voltage-controlled voltage source. And because it's a voltage source, we don't know its current, and therefore we don't know how much current is coming out of this op-amp. There's no way to determine that without solving the entire problem. So we won't try to do that because it would be an error. And if I select that, for example, it'll just give me an error. Instead, we're going to write a KCL equation for node 2. So I'll select node 2 there, and that's allowing me to do it. So basically, node 2, remember that it might look like there's 3 things connected. There's the 9 ohm and the 6 ohm and the negative input. But again, we have to remember there is no current through that negative input for an ideal op-amp. And a real op-amp might have a very small current there, like picoamperes or something, but it's not going to be important for our purposes. So we're going to neglect that entirely. So we want the current out through the 9 ohm and out through the 6 ohm, for example, or we could go in if you prefer. So going out through the 6 ohm, that's just that V2 divided by the 6 ohms. And then going out through the 9 ohm is a difference of voltages divided by the 9 ohms. And that will have to sum to 0. So we just click those terms. And so we'll just fill in the blanks now. V2 divided by 6. And here we have V2 minus V3 divided by the 9. And that represents, again, the current going this way. And this represents the current going this way. So we'll check that equation, and that is correct. And we have the basic equations we need now. We have 3 unknowns, V1, V2, and V3, and we have 3 equations involving those variables, so that is sufficient. However, we also need equations for the 2 SOT variables. So we'll select, first of all, a SOT branch power, because that power in the 6 ohm resistor is a branch power. Basically, it's across a single element. And it reminds us here that we have 3 sets of terms we can use if necessary, which are sometimes needed. In this case, I don't think we'll need the others, but if you need them, they're there. And so we're going to write P dissipated in the 6 ohms equals, and then we say, well, that's basically a voltage connected to ground. And so using the formula for power dissipated in a resistor, just V squared over R, that's convenient to use here since we know the V, or we're going to know the V. And so we can just make that V2 squared, since it's subtracting 0 from that for ground, divided by the 6 ohm. And that will be the standard equation for power dissipated in a resistor. So we'll check that. And next, we need to have the output voltage, which is V3 measured with respect to ground, or 0. And that's not a branch voltage, really. So it'll be classified here as a non-branch voltage, a SOT non-branch voltage. If you try to write a branch voltage, it'll tell you that there isn't one. So we have V3, 0, and that equation for that is always very simple. It's just V3 minus 0. So it's really just V3. And we'll check that. Okay, so now we have all the equations we need. We can just click no more equations here. And now it is going to have us go through the exercise of simplifying the equations and putting it even in matrix form. None of that's probably really necessary for this problem, and you could skip all of it if you want. You could have really just entered numerical values here if you know the answers, which frankly would have been quite easy, and maybe I'll demonstrate that for another problem at the end. But we can enter these equations. So the V1 equals 5 volts. That'll be a coefficient of 1 for the V1, and then we just put a 5 for the constant term. That expresses that equation. V1 minus V2 is equal to 0. Well, I have 1 times V1, and then we'll have a minus 1 times V2. Or we could multiply that, both of those, by any constant if we wanted, but there's no reason to. And then for the third equation, we have no V1s, so we'll leave that at 0. And then V2, we have 1/6 plus 1/9. Well, we know that 1/6 is, we have to make a common denominator here. So we have 3 times 2, 3 times 3, so it'd be 18 would be the common denominator. And so this would be 3/18, and this would be 2/18, and so that's going to be 5/18 for the V2. And in fact, we can now enter that just as a fraction if we like, to get rid of that 0. And Circuit Tutor now evaluates fractions here for you. So that's 0.2778, or you can do it on a calculator and just enter it yourself if you like. And then for V3, that's minus 1/9. And so we can just type minus 1/9 there. As long as it's a simple numerical fraction, it will accept it. It won't accept a complicated expression, but it will accept a simple numerical fraction. Okay, and that's all equal to 0. And again, it converts it automatically to a decimal for us. So now we'll check those equations. And they are correct. And now it's just asking us to do the matrix form, which here we can really just click this copy button, would be the easy way to do it. Otherwise we could type them in manually, but that would take longer. So I'm just going to do it this way. And we'll check that. And that will necessarily be correct. Okay, so now it's going to advise us to work this on hand, which really is quite simple. You can almost do it in your head, but so we know the value of V1 is just 5, so we'll just put that in here. And we know the value of V2 has to be the same as V1, so that'll also be 5. So they're both at 5 volts. And the only one that's hard at all is V3. And really it's not very hard because, again, if you're trying to do Gaussian elimination here or something, I think you're really looking to make this a lot harder than it is. But we could just take this equation and substitute 5 in for V1. Well, it's not even used, so we don't need it. But we can substitute in the V2 equals 5 into this equation, and that'll give us 5/6 plus 1/9 is equal to V3 over 9. And then we can just work out what that is. And I'll just do that real quickly, and I can also use the formula for non-inverting amplifier. So 5 times, well, let's see, we have 9/6. So that's a gain of 2.5 times 5 is 12.5. So I'll just put in 12.5 volts there, which again, you can do that very simply on paper if you need to. And we'll check that, and that is correct. Okay, and then finally, we're just going to evaluate the sought variables. And so the power dissipated in 6 ohm resistor, that's just V2 squared over 6 ohms. So that's just going to be 25/6, basically, we can see, and we can enter that again as a fraction. So we just type 25/6. Now, it won't allow you to square things or that sort of thing. You have to do that yourself. But for simple fractions, it'll allow that entry, and it converts it automatically here. And then the V3 is just 12.5, since it's the same as V3. And now we can check those, and that is correct. And it will always create that PDF transcript showing both correct and incorrect steps for you to review later. And you can also get a detailed explanation if you wish, or you can just click no and leave the problem, but I'll just show it for for the sake of completeness here, and you could even see Gaussian elimination steps if you want to, although again, I don't recommend doing that here. Now, I will show you just sort of a cheat, if you will, because this is a standard non-inverting amplifier, where we have this type of configuration where the input voltage is connected to the positive terminal, and then we have a feedback resistor and then a resistor to ground. The formula for that, derived in the introductory tutorial, is just the gain is 1 plus 9 divided by 6, which is 3/2, or 1.5. So that plus 1 is 2.5 is our gain. And again, multiplying 2.5 by 5 will directly give us the V3 value that we went through all these equations to get. And that's just going to be 12.5. So we could have just entered that at the very beginning and saved us all this trouble. And then the power dissipated here, well, the V2, we know that has to be 5 volts because there's no voltage drop here. So it has to be the same as the fixed voltage here of plus 5. And so since that's 5, again, you could have just taken the 5 squared over 6 and kind of done that almost immediately. And you could have entered those instead of all these equations and everything, just as sought variable equations with numerical values. And that could save you some time, but you can also do it the way that I showed here. Okay, so I'm going to exit that, and again, the review work button will allow you to see the transcript of your file. That completes this problem.